OK, bonjour tout le monde. Merci d'être venu. Thank you for coming. So, up to now, we have discussed what is measured in experiments. We have, in scattering, we have the fluctuations. And for response functions, we have susceptibilities, or linear response functions. So, in that case, to ensure causality, we need to have these spectral representation of the retarded function, and this is for causality. Now you see that the physics, whether you want scattering or response function, the physics is in this Kidable prime. We saw the other day that what comes into Kidable prime are the energy, the eigen energies in denominators and matrix elements. So the matrix, depending on the operator that are here, you would get different matrix elements. So depending on the measurements, you couple to the many-body system differently. And so starting next week, we will begin slowly to see how to compute these quantities. But before we do that, I want to show some important general properties of this. This is useful for several reasons. One of them is that there, as I said last time, there are very few things that we know exactly. So we might as well write them down and use them as constraints, some rules. And then if we have some phenomenological representation of these response functions, we might as well do that in a way that is most respectful of these constraints. Okay, so that was the fluctuation dissipation theorem that relates these fluctuations to this quantity that is dissipation in many cases, and the response function. So I will start by establishing something that's called a thermodynamic sum rule. I will show that the order of limits is important. The limits are Q and omega goes to 0. Which one goes to 0 first makes a big difference. Then I will show you that the high frequency behavior is related to moments of this Kidable prime. And in particular, we will see that in the very high frequency limit, we recover the free particle behavior, like we did for the harmonic oscillator. And then the Epsom rule is used a lot in the optical conductivity. For example, experimentalists use that all the time, and we do as well. So we might as well use that very famous Epsom rule. And then hopefully I will start the Kubo relations, which in fact we've already derived here, but we will derive in the context of coupling to the electromagnetic field, which is a non-trivial matter that I will discuss hopefully today a little bit. So are there any questions for last time? No? Okay. So let's start with the thermodynamic sum rules. So you know that the expectation value of the number operator, the thermodynamic average and expectation value at the same time of the number operator is a trace, and then the grand canonical ensemble e to the minus beta h minus mu n times n divided by z, where z is just a trace of e to the minus beta h. So suppose in thermodynamic I want to compute 1 over beta dn d mu at constant temperature and the volume. So this is at constant volume, so that's fine. So constant temperature, I just need to take the derivative of this. Okay, because in thermodynamic, n has to be interpreted as a statistical average. Okay. So if I take this derivative, what do I get? I get n, right? Because the minus is plus. If I differentiate with respect to mu, I get beta n, and I have beta here. And n commutes with itself, so that's no problem. Is that all that I obtain? No, huh? Nicolas says no, why?
Do you have to derive by the z by
Yes,
whatever we're, yeah?
exactly. So you need to differentiate the z as well. So that will give minus the expectation value of n squared. I will let you do this little calculation, and it's a very important calculation because we will use this all the time with Green's function and everything. So in the sense of that, not forgetting this denominator. So these are really the fluctuations, if you want, of density. but you see that if I integrate S over all frequencies, forget about the right-hand side for now. I just integrate the density correlation function over all frequencies. I get the equal time correlation function, namely, I get this. Okay, but this is evaluated that Q goes to 0 in the sense that the N here is uniform. It doesn't, it's N is the total N. So it's not the Fourier, if I think of N as the Fourier transform, it's Q equals 0, means integral over all R. You will see that it turns out that the limit omega and Q goes to 0 are very delicate. So what I have really is that the limit Q goes to 0 of S and N of Q and omega integrated d omega over 2 pi. That's this quantity, so it's equal to 1 over beta dn d mu at constant temperature and volume. Okay.
Excuse me.
Yes.
I didn't understand this. Why are they equal?
It's because S of nn is just equal to the Fourier transform of the density at point R and time t correlated with n at time at some position 0 and sometimes 0. Okay. So if I integrate over all, if I take Q here, it means that I am integrating e to the I Q dot R, right? dr minus sign. So it means that becomes the total density. Okay. So I'm back to this density correlation function. And S is defined, if you look at the definition, if you go back to the definition, n is defined as the correlation function of this, but not only this, I should have written n minus, I should have written delta n. In other words, the deviation from the average. These are the fluctuations, so it's the deviation from the average. So the deviation from the average is this. And so when I take, I take integral over all frequencies, it means that in the end I get equal time. Okay, so that's why I do the integral over frequency. Is this okay now?
Yes.
Thank you for the question. Don't hesitate. If you have questions, you ask. So now let me use the fluctuation dissipation theorem. So if I use the fluctuation, the dissipation theorem, I get that the limit q goes to 0. And here is the magic. The point is that in the limit q goes to 0, this becomes this becomes proportional to a delta function of frequency, this quantity. I will show you in a moment. So the point is that as q goes to 0, then the frequency here becomes very, very small. So it means that I can expand here. And I get integral of d omega over 2 pi. And when I expand, the h bar disappears. So I have 1 over beta. And then I have chi double prime over omega. Chi double prime and n of omega. And the omega is still there in the denominator, divided by omega. And that's equal to 1 over beta dn d mu of the t v. So that's called a thermodynamic sum rule. It's a sum rule. It just means that you integrate over all frequencies. So if you compare with this, you see that it's equal to the response function at omega equals 0. So the question is, why can we get rid of the iota? So if I take omega equals 0, then when I compute the iota, it gives me a delta of omega prime. But chi double prime at 0 is 0. So the iota is not necessary anymore. So this is really equal to 1 over beta times chi retarded of q at 0 frequency. So it's equal to the limit q goes to 0. Like this. So here it's n. So another way to see this is that if you have a perturbation that is there for forever, so at 0 frequency, then it's a thermodynamic response. You're just, looking at how the density is modified when you change the chemical potential. And it is what we call a reversible process in thermodynamics, right? When we write that dE, so the change in energy, for example, is equal to TdS minus PdV plus mu dm. Then these, for example, if you compute dE dt or dN dt, all of this is reversible. It's quasi-static. So in the end, that's why we don't need the iota. So any quantity, here I should have worked with the grand potential here, but okay. So any quantity, if I look at chi retarded, for example, it's the quantity AI that responds to some operator AJ that's coupled to field little aj, then this is related to this. So
just so you know, it's barely readable.
let me try to put it somewhere else. So the only thing I'm saying is that this can be generalized. When you look at the thermodynamic variables. So if here I add the AI and AJ, I would have AI in the numerator and the conjugate to this variable in the denominator. Okay, that's all I'm saying. I'm saying this is more general than what I just wrote. So let's think a little bit about this point here, the order of limits. So if you look at chi double prime n at q equals 0 as a function of time, it's equal to 1 over 2 h bar. I just use the definition. 1 over 2 h bar times the expectation of the commutator of n at time t with n. Okay. So what is this? This is 0. Why? Because the Hamiltonian, by hypothesis here, commutes with n, conserves the number of particles, which means that n is independent of time. You see? If I write the evolution operator, if I write e to the iht over h bar and e to the minus iht over h bar, and n commutes with h, it means that the time evolution disappears. So that's independent of time. And an operator always commutes with itself. So this is equal to 0. Okay. So you see why it was important to take the limit q goes to 0 at the end. So let me give you an example of a calculation. I've just given you the result, so you will see it is instructive. So if I look at the chi double prime n as a function of q and omega, in the low frequency omega goes to 0 and q goes to 0 limit, it's equal to 2 times the diffusion constant times the q square times omega over omega square plus dq square times chi and n, where chi and n is this thermodynamic derivative. So you see the problem very well, right? You see that if I look at the chi double prime of q omega, and I divide by omega here to put it in this sum, you see that when q goes to 0, it becomes a delta function of omega. Okay, so that's why I was able to use the low frequency limit here in this case. So what happens if I take the Q goes to 0 limit? I get 0. If I take Q goes to 0 before omega goes to 0, I get 0. Why is that? Because if I take Q goes to 0 first, this commutator is 0 all the time. Okay, so that illustrates very well, what happens with the order of limits. So the order of limits is always very delicate. And for thermodynamic, it's also always the 0 frequency limit first. And it turns out that for example, conductivity, like we will see later, conductivity is the opposite limit. Conductivity will be related to current correlation function. And we will need to take the Q goes to 0 limit first. So the Q goes to 0 limit first is like having an infinite volume. And having an infinite volume allows us to have a frequency response, even as omega goes to 0. The spectrum can become continuous. So this, in some sense, this is deeply related to having an infinite system and having sort of peculiarities that arise in this infinite volume limit. Okay. So now, do you have any questions?
So we said that the Q goes to 0 first is for the electric current, but is there
No, Q goes to 0 limit is for first is for dissipation in general.
Okay, so
for current, DC current or DC heat transport, all the transport coefficients are obtained by taking the Q goes to 0 limit first. That's what I'm saying.
okay, thanks.
Okay. And we will see that the DC conductivity is related to current correlation function. That's the subject of the next point. Okay. So let's look at what happens now at very large frequency. So I'm talking about point 3 here. And let's see if we can see anything about what happened at large frequency for these functions. And what I'm saying now will be valid. The same type of reasoning will appear for Green's functions later. Okay. So you saw that for this chi double prime in the numerator, I have some matrix elements. And eventually, the response at sufficiently high frequency, there will be no dissipation. Okay, the states will be too different from the matrix element will vanish. In other words, if these momentum states are eigenstates for, in some sense, I mean, not far from eigenstates for non-interacting system. But even, in fact, we will see for non-interacting system, this has a limit. Eventually, for any finite Q, it will vanish for some sufficiently high frequency. So what happens if I am at sufficiently high frequency? At sufficiently high frequency, the Ieta becomes irrelevant. Okay, because the Ieta gives me a delta function, and I know this vanishes in the infinite frequency limit. So I can write that the limit of omega goes to infinity, in fact, not equal infinity. This is not a really nice notation. It's limit omega large. Let me write it this way. Omega large. Where is my... okay. I need some space. So limit omega large. What I mean large is omega much larger than lambda, where lambda is the largest frequency where this is different from 0. Okay, then I think it's a clear notation of chi RR of any variable AI AJ. Let me drop the Q because here the Q will not be so relevant. Okay, but it's under. If you want, you can think of the Q as being in the IJ. Chi double prime of omega is equal to minus sum d omega prime over pi of chi double prime of AI AJ of omega prime divided by omega times 1 minus omega prime over omega. Okay, I just no iota, I just rewrote this denominator. But now omega prime will be always less than omega. Why? Because this is bounded by a bounded spectrum here, and I'm looking at omega much larger than lambda. So it means that the Taylor series of this will converge. So the Taylor series then is equal. Remember that this function is odd. So this function is odd, which means that only the odd values of omega prime will survive. So that would be minus 1 over omega to the power 2n of the integral of d omega prime over pi of omega prime to the power 2n minus 1 of chi double prime of AI AJ of omega prime. Okay, all that I have done is the power series expansion of the denominator, and I have kept only the odd terms.
Yeah, you just forgot the summation sign.
And I forgot the summation sign. So it's sum over n. Okay, but it turns out that this quantity, these are called moments, if you want. Moments of this function. These moments can be calculated from equal time commutators. And equal time commutators we can compute. If it's not at equal time, it's more complicated. You need to see how the time-dependent operator evolves and then becomes complicated. But at equal time, we know how to compute things. So how can we compute this? So the integral d omega prime over pi. This I can write as I. Okay, let me focus just on this piece. Okay. So I can write this as d omega prime over pi of I d dt to the power 2n minus 1 of e to the I minus I omega prime t times chi double prime of AI AG of omega prime. And this quantity has to be evaluated at t equals 0. Okay, if I take derivatives here, 2n minus 1 time, okay, minus I that will cancel every time, and I will get omega prime to the 2n minus 1. Okay. And when I evaluate that t equals 0, I get rid of this. So I get this. Okay. Now I'm going to assume that I can interchange the order of limits, which is okay when the Fourier transforms exist. So so once I do the the time derivatives, you see that this will be equal to so this will be equal to I times let me take yeah, okay. Be equal to the expectation value of I d dt to the power 2n minus 1 of a I of t a j evaluated at t equals 0. Okay, because that's the here I'm taking the IDT I'm taking outside, and this is the Fourier. I'm going back to time here. Okay, and when I go back to time, I get AI of t aj, and outside I have the IDDT to the power 2n minus 1. Okay, that makes sense. And that has to be evaluated at t equals 0. But why do I say that we can evaluate this from equal time commutator? Well, because IDDT is just using the Hamiltonian. So I d dt of e to the I h t over h bar, the I e to the minus I h t over h bar, that's equal to minus 1 over h bar times the commutator of h with the AI. Okay, so I can keep using this. I can take more and more derivatives, and then at the end I evaluate at t equals 0. So when I evaluate at t equals 0, then these have disappeared. Okay? When I differentiate, I should keep. If I just take the derivative, I should keep the e to the I h t over h bar ai e to the minus I h t over h bar. So I can keep taking derivatives. So that will be the commutator of h with the commutator of h with a. You see, the commutator in the end I get commutator of h with the commutator of h with the commutator of h with ai. That would be the third order derivative. Okay. And then I take t equals 0. So when I take t equals 0, these evolution operators disappear. And equal time commutation relation, I know what to do. Okay. So high frequency expansion of the susceptibilities are given by moments of chi double prime. And these moments of chi double prime can be computed from equal time commutators. That's the lesson. Now let me compute, let's look at the Epsom Rule. So the Epsom Rule, as I said, we will come back to that a number of times in the electron gas, in the optical conductivity. It's one of the important sum rules. That's an exact result. So the Epsom Rule is given by it corresponds to the second moment here, n equals 1. So I have 1 minus 1 over omega square times this integral, okay? So that's integral d omega prime over pi of omega prime chi. Okay, now I need to specify. I'm going to specify that I'm looking at the density correlation function at Q. I'll drop the arrow like I did earlier. Chi N of Q and omega prime. And what I will show is that this is equal to minus n q squared over m, where n is the density. Okay, so little m is n divided by volume. Number of particles divided by volume. So that's the density. And m is the free electron mass. So this will be modified when in tight binding models, but if we stick to the exact result here, where we just don't restrict the integral to a given band in the system, but we really go to infinity, then we get this, and this is the free particle behavior, right? It's the free mass that comes here. So that's what we said for the harmonic oscillator, that at high frequency, the behavior is that of the non-interacting system. And the concept, you will see that the reason for this is because of it's just because of current conservation. So it's a rather deep result. So let's look first at what we mean by n of q, n of minus q. Okay. So if I look at, so that's chi double prime. So if I look at just some definitions, so suppose that I write n of q. Forget about the time now. I'm focusing on the spatial dependence. So I take n of q, n of minus q, 1 over volume. Okay. This quantity is equal to 1 over volume times integral d cube r e to the minus I q dot r times n of r. And then the other, this n of minus q is the integral d cube r prime e to the I q dot r prime times n of r prime. Okay. So if I have translational invariance, What does it mean? It means that this correlation function depends only on r minus r prime. And here, yes, right, depends only on r minus r prime. So it's fine here. I have e to the minus iq r minus r prime. And the center of mass, if I go to coordinates that are r minus r prime and r plus r prime over 2, okay, so this is relative coordinate and center of mass coordinate. I can integrate over the center of mass coordinate, and that will give me volume. Okay, that will simplify this volume. So all that I'm saying in this little side comment is that this quantity is just equal to integral d cube r e to the minus I q dot r times n of r n of 0. Okay, so the Fourier transform of this that depends on the time difference only is the same as taking Fourier transform of one, Fourier transform of the other, and divided by them. Okay. This is the same thing I did with frequency when I had the total time appearing. Now I have the volume. I was using time translational invariance. Now I'm using the wow. Okay, not much time to prove the Epsom rule. Okay, so like before, let me focus on the just on this. Okay. So if I focus on this piece, then it's equal to this is equal to this red is equal to 1 over volume times the commutator of I I dn dt of n, but we said that this is just equal to minus the commutator of h with the n of q, and the whole thing is commuted with n of minus q. So I have the commutator of the commutator, okay? And I have some h bars that come in also. H over h bar. I times I gave me -1. Now, H has a kinetic energy part and it has a potential energy part. Okay. So what happens to the potential energy part? Does it commute with n of q? The potential energy involves only density. Think of the Coulomb interaction. And density commutes with density. So the only piece that will not commute with the Hamiltonian is the kinetic part. So what we need to compute for H, so H kinetic, if you want, is equal to sum over all the particles. Let me call them beta equals 1 to, well, here I'm confusing, 1 to n. N is the total number of particles of p beta square over 2m, okay? And there are three components for each particle. So there's an additional index here. So let me start by computing the commutator then of the P beta with n of q. So what is n of q? N of q is equal to the integral dq bar e to the minus I q dot r times delta of r minus r alpha sum over all particles. Sum alpha equals 1 to n. Okay, that's the r is the position operator for particle alpha, and this is a vector also. Okay, so that's measuring the density at position r. So the integral I can do, all that happens is that I'll be left just with the exponential. Yeah. So if I do the integral, I just have the delta function disappears. I'm left with the sum over alpha. And I have r alpha here. So now to compute the commutator of P with r alpha, P is h bar over I times grad, h bar over I times the grad with respect to particle beta. Okay, this is not the direction of the gradient, this is particle beta. So if I do this, I have a minus sign that comes out, and I have minus h bar. And I have, so the commutator will be different from 0 only if alpha equals beta. Okay. So when I do the sum over alpha, only the beta part will contribute. The I here simplified, there's minus sign, there's h bar, and the only thing that I get is q, and e to the I q dot r beta. Okay, so that's just acting with the gradient of this.
Is there a minus sign missing?
Yes, in the exponential. Thank you. Okay, so that's I'm still computing just this, right? Now I need to look at the p square. What happens to p square? So if at once I have p square beta commutator with n of minus q, this is just equal to p dot p beta n of minus q plus p beta n of minus q dot p beta. Okay, usual thing for commutator of products. So let's continue this job here. So when I compute this, okay, I'm just computing with this. So I get sum over beta. And then the two commutators will be equal, okay? And then I multiply from the left and from the right, it will give me the same thing. So the 1 over 2m, I will stay 1 over m. And then I found that when I take the commutator of beta with n of q, I get e to the minus iq dot why? Oh, sorry, I'm supposed to be doing this here. N of q. I'm doing the first one. So the first one, I'll be left with, I've got rid of the factor of 2. I'm left with p beta of minus h bar q so there's a dot product, e to the minus I q dot r beta. And the other term with dot p beta. So the same thing with p beta. And now I have to compute. I have to compute the commutator with n. All that I did now is this piece, right? I just did this. Now I need to do this commutator, so I have some p beta left. But I know how to compute p beta. So I'm short of time, but I will let you work the details to see that I'm not cheating. But you see what will happen, right? When I compute now the commutator of p beta with n of minus q, I will get again q e to the this time plus iq dot r, okay, because I have a minus q there. So so the sign will change here, but I will get another factor of q. So this is how I get q squared. This is how I get n. And the n, why do I get the total number of particles? Because I'm still left with the sum over beta. And all the terms will be identical. So the sum over beta will give me the total number of particles. And the total number of particles divided by volume, which is still there, is equal to little m, the density. So that's how this story finishes. Okay. And the h bar here cancels that h bar, and that's the only h bar in the way. So there's no h bar dependence here. Okay. So I'll let you work out the details to be sure there's no mistake, but it's, I mean, I think you see what's happening, why it's doing this. Any question? Okay. So next time we will see how to couple the electromagnetic field in a gauge invariant way with the Schrödinger field and find out which correlation function we need to compute to get, for example, the conductivity, optical conductivity, and what is the correct order of limit. And we will see that when we look at the response of the electromagnetic field, there's a transverse and a longitudinal response, right? Because the vector potential has longitudinal and transverse components. So we'll have the same thing, okay? So when you have a vector, you know, this is a transverse response, for example, in a wire. And the longitudinal response then would be to, so that there's some Q dependence, you see some wave vector dependence and some position dependence that is perpendicular to the direction of the vector. So that's the transverse response. And in a wire, it's a relevant thing. And the longitudinal response for a vector is that, right? So the dependence is along the direction of the vector. So Joe, I remind you that for a longitudinal vector, it's a gradient of lambda. The curl is 0, and for a transverse response, the divergence is 0. Okay. So see you Friday then. If you have some questions, I'll stay around, okay? So you stay and you ask questions. I will stop the recording.